Okay, good morning. First, an announcement. Next week, on Wednesday, there will be lecture instead of exercise course. So there will be 3 lectures next week, but there will be no lecture in the week after because I will be at a conference. So next week, there will be lecture on, well, also on Wednesday. And Wednesday is the 20th. And in the week after, there will be 2 exercise courses and no lecture. Okay, so where are we? We discussed the semantics of Haskell. We introduced a subset of Haskell called simple Haskell. And we've also shown how to translate complex Haskell programs automatically to simple Haskell programs. And using this translation, we defined the semantics of simple Haskell programs, and by the translation also of complex Haskell programs. And after having discussed the semantics of Haskell, we will now turn to the implementation of Haskell. And what we will do is we will implement an even more tiny little subset of Haskell. And we will show that complex Haskell can be translated to simple Haskell, and simple Haskell can be translated further to this tiny little subset. And this tiny subset is called the lambda calculus. And that's also the topic, the name of the next chapter, the lambda calculus. So historically, the lambda calculus is much older than Haskell, or in fact much older than any programming language. So the lambda calculus was developed by Church, by Alonzo Church in the 1930s. So it's much older than programming languages. And the reason why Church developed the lambda calculus was that he wanted to have a model to explain computability. So I mean, they didn't really have computers in that time, but they were thinking about what could a machine do. And different people developed different models of computation. And Church developed the lambda calculus in the US. And his goal was, so the goal was describe a model for computability. Computability. So Church said that, well, he developed this calculus, and every function that can be computed in this calculus is computable. And now around the same time, or a little later, Alan Turing did something similar in England. He also had the same goal. He wanted to describe a model for computability, but he came up with a different model. So more or less in parallel, Alan Turing did the same. So Alan Turing developed another model for computation, namely Turing machines. So he developed Turing machines for the same goal. And then, of course, they compared their models and they found out they compute exactly the same. So every function that you can compute with the lambda calculus, you can also compute with Turing machines and vice versa. And that led to Church's thesis. And the thesis is that no matter which model you take, the set of computable functions is always the same. And indeed, this is true also for all the programming languages that we know nowadays. So no matter whether you take lambda calculus or Turing machines or Haskell or Java or Prolog or C or whatever, the set of functions that you can compute is the same. Now, it's not that you can compute something in one language and you cannot compute it in the other. It might be more or less efficient, or it might be more or less cumbersome, but as far as power is concerned, they are all the same. So it turned out that the functions computable by the lambda calculus, they are the same as the functions that are computable by Turing machines, are the same as the ones computable by Turing machines, or by any other sensible model of computation. So Turing machines, Haskell, Java, C, whatever. So any sensible programming language can compute exactly the same set of functions. And so this leads to the conclusion that this is the set of computable functions. I mean, you cannot prove this, so maybe one day somebody comes up with a new language and a new computer that can do more, but it's rather unlikely. So this is sometimes referred to as Church thesis, and it states that this is the set of computable functions. And no matter which machine you design, it will never be able to compute more than this. I mean, it might be able to compute less than this. If you design a stupid language, maybe it can do less, but it won't do more. So this is the set of computable functions. Okay, so this is the history of the lambda calculus. But in contrast to Turing machines, the lambda calculus can really be used as the basis of sensible programming languages. I mean, a programming language which builds upon Turing machines, yeah, you can design this, but whether this will be very popular and very useful is doubtful, because Turing machines are a nice theoretical model, but you don't want to program in Turing machines. But you want to program in the lambda calculus, maybe not in the purest version of the lambda calculus, but if you add some more syntactic sugar, then it can be fun to program in the lambda calculus. And indeed, this is functional programming. So functional programming languages are essentially syntactically enriched versions of the lambda calculus. And the first functional programming language, Lisp, developed by McCarthy in the 1950s, had exactly this idea. So he built upon the lambda calculus, which was well known at that time, and his goal was, let's make a real programming language out of it. So in contrast to Turing machines, the lambda calculus is not just a theoretical concept, but it can be used for something practical. The lambda calculus can be used as the basis of real programming languages. Well, I mean, Turing machines can be used as well, but it makes no fun programming in Turing machines. As the basis of real programming languages, and that's in fact the origin of functional programming. So this leads to functional programming. So indeed, functional languages like Haskell, they contain the lambda calculus and they add a lot of syntactic sugar. So languages like Haskell, in fact, are just extensions of the lambda calculus by syntactic sugar, which make programs more readable and which make it nicer and more convenient to actually write programs of the lambda calculus. By lots of syntactic sugar. Well, not just syntactic sugar, but mostly. And so when we think about implementing functional languages, we can proceed in the following way. So for the implementation and also for type checking Haskell, and type checking of Haskell, we can proceed as follows. We take complex Haskell programs, so which contain all the features of Haskell, and we first translate complex Haskell automatically to simple Haskell. And simple Haskell is the subset of Haskell where essentially pattern matching is missing. And we discussed how to do this. So by adding some more predefined functions, these ISA and ARCOF functions, which recognize with which data constructor an object is built and which can extract the arguments of data constructors, we can go from complex to simple Haskell automatically. And now we will compile this even further. So simple Haskell can be translated further to the lambda calculus. How to do this, we will see in this section. And, well, this you can see as a kind of compilation. So we go from Haskell to a kind of machine language, namely this one. And then afterwards, we just need some implementation for the lambda calculus, which executes this machine language. So this all works automatically. And then one only needs an implementation of the lambda calculus, and that is pretty easy. Of the lambda calculus. And indeed, we'll try to do something like this on the next exercise sheet, which will be distributed at the end of the week. So that's end of next week. So that's the idea. So the lambda calculus is in some sense the machine language of functional programming, the bytecode of functional programming, if you want, of functional programming. And we do the same thing for type checking. So instead of checking whether this complex Haskell program is well typed, we translate it to lambda calculus, and then we check whether the resulting program here is well typed. So that's the idea. And well, the nice thing is that although the lambda calculus is such a small and tiny language, it is still a full programming language. So it is Turing complete. You can still program all computable functions in the lambda calculus. So that's the goal. And what will we do in the subsections? Well, we will first introduce the lambda calculus. So this is a very tiny programming language, and we will introduce the syntax of the lambda calculus in the first subsection, but this will be very easy and very quick. We will also introduce the semantics of the lambda calculus, and we could do this again in a denotational way, but to show you the different versions of defining semantics, here we will do it in an operational way. So this means we will give an implementation of the lambda calculus, one standard implementation, and well, this implementation describes the semantics of the lambda calculus. So this will be the operational semantics of the lambda calculus. So this will also be very easy. Of the lambda calculus. And then we know what the lambda calculus is, so then we only have to describe how this step should work, how we can go from simple Haskell to the lambda calculus. So translation from simple Haskell to the lambda calculus. And then in the last subsection, I will speak about possibilities to reduce the lambda calculus even further. So I mean, it's a tiny language, but it still contains some syntactic sugar, and if you wanted, you could even throw out more, and then you arrive at a subset of the lambda calculus called the pure lambda calculus, and that is still Turing complete. That is still a full programming language, but then things that get really unreadable, but it's interesting to see how much you can go and you still have a full programming language. So this will be the pure lambda calculus. So this is even less than the lambda calculus. Okay, so learning another full programming language sounds challenging, but it is not challenging. So the syntax of the lambda calculus is very, very easy, and we can easily do this on one slide. So let's start with this. Let's introduce the syntax of the lambda calculus. Of the lambda calculus. And the syntax of the lambda calculus, so the programs of this tiny little programming language are terms, so-called lambda terms. So the syntax are the so-called lambda terms. And what are lambda terms? Let's define it. So what are the lambda terms? So the lambda terms are built over a set of variables and a set of constants. So let C, calligraphic C, be a set of constants. These constants, they stand for function symbols and a set of variables. And V, a set of variables. And then, and this set should always be infinite. So an infinite set of variables. And now we can build the set of lambda terms. The set of lambda terms. And we denote this set by capital lambda. So the set of lambda terms, capital lambda, is the smallest set with the following four properties. All constants are lambda terms. So all these constants, we regard them already as lambda terms. So all constants are lambda terms. All variables are lambda terms. So these are the most basic lambda terms, variables or constants. And if we already have two lambda terms, we can build new lambda terms by applying one term to the other. So if we have two lambda terms, T1 and T2, we can apply T1 to T2, and we do this by just writing them beside each other. So this is exactly as in Haskell. If you write two terms beside each other, the idea is that you apply the first one to the second one. So this is also a lambda term if T1 and T2 are lambda terms. And there is one last possibility to create lambda terms. And, well, I mean, the name lambda suggests that somewhere this Greek letter should appear. And indeed, the last possibility is the reason for the name lambda. So you know in Haskell that we can use these lambda abstractions to denote functions. And in fact, this notation comes from the lambda calculus. So you can write the following: lambda x dot t. And this is also a lambda term if x is a variable and t is a lambda term. So this means exactly the same as in Haskell. So in Haskell, you would write backslash instead of lambda because we have no lambda on our keyboard. And instead of the dot, you would write an arrow. But what you write in Haskell like this is in the lambda calculus written like this. And that's it. This is the set of lambda terms. So there's not really anything new. I mean, these are expressions that we know already from Haskell with a slightly different syntax, but that's the historical syntax that Church used. And that's enough. You don't need more than this to write any program. That's surprising, but we will see this later on. So terms of the form where T1 is applied to T2, they are called applications because, well, here the first term is applied to the second one. Are called applications. And terms with such a lambda, lambda x dot t. Well, this stands for the function that takes this variable x and gives you this term t as a result. This is called a lambda abstraction. These terms are called lambda abstractions. And for the constants, we can use arbitrary symbols. So for the constants in C, we use arbitrary symbols such as suc 0 is a suc, or square root, or whatever. So those things that should denote functions, we take constants. So the constants play the roles of functions. And when we want to translate simple Haskell to some lambda term, then those function symbols that we had in our simple Haskell program will be turned to constants. So if our Haskell program contains these function symbols, they will somehow occur in the Haskell term, in the lambda term as well. Now to ease the writing of these lambda terms, we will make some conventions concerning brackets and concerning the scope of lambdas. So we use the following conventions to avoid writing too many brackets. So the first convention is that applications associate to the left, like in Haskell. So applications associate to the left. What does that mean? That means that if I write T1, T2, T3 without brackets, then this stands for first apply T1 to T2 and then apply the result to T3, like in Haskell. So application always associates to the left. The next convention is that if you have a lambda, then the question is, how far does the scope of this lambda go? So this lambda x, where does this bind the variable x? And the convention is, it binds it as far as possible. So the scope of a lambda goes as far as possible. So to illustrate what I mean by this, suppose I write the following term, lambda x dot xx. Now this is a legal Haskell term. Why? Because x is a variable. And if x is a variable, then xx is a lambda term. Because I can build new lambda terms by writing two terms beside each other. So this means x is applied to x. Whether this makes sense or not is a different question, but at the moment we are just concerned with the syntax. And the syntax allows us to apply any lambda term to any lambda term. There is nothing like types here, not yet. So we can apply terms to terms, so we can apply x to x. So xx is a lambda term, and I can create a new lambda term by writing lambda something before it. So lambda x dot xx is also a lambda term. And now the question is, which of these x's is bound by this? So does this stand for, is this lambda x dot x applied to x? Or is this lambda x dot, and now xx applied here? So if I don't write brackets, do I mean this or do I mean this? And well, the scope of a lambda goes as far as possible. So it goes not only to this x, but also to this x. So this means this. The lambda binds as much as possible, and here this lambda x could also concern the second x. So if we don't write brackets, then we mean this. So that's the second convention. And the third convention is that we can also write several variables behind the lambda. So we may also write lambda x y dot t, and that's the shorthand for lambda x dot lambda y dot t. And of course, the x binds as much as possible, so this stands for lambda x dot lambda y dot t. So if there's an x in this t, it is also bound by this lambda. Okay, so these 4 lines up there are the whole programming language. That's enough for programming. You don't need all the rest of Haskell. Okay, it's probably cumbersome to write programs in the lambda calculus, but it works. And how to do this and what this means, how the semantics is defined, we will get to this in a few minutes. But in order to describe this, what these lambda terms really mean, we need some more notions. And one notion that we need is, again, the notion of free variables. Now, we had this already for Haskell expressions, and it works exactly in the same way for lambda terms as well. So there's not really anything new. But since we only defined it for Haskell expressions, let's define it for lambda terms as well. So what does it mean that a variable in a lambda term is free? Well, it means that this variable is not bound by a lambda. So what are the free variables of a lambda term? Of a lambda term. Well, for any lambda term, so for any term t, which is a lambda term, so which comes from capital lambda, we define the set of its free variables. So free of t, and this is a subset of the variables. Okay, and what possibilities do we have for lambda terms? Well, lambda terms are either constants, variables, applications, or lambda abstractions. So 4 possibilities, and let's define it for all possibilities. If I have a constant free of c for any constant c, so for example, if I want to know what are the free variables in the function symbol suc. Well, there are no free variables. So free variables have to be, in particular, they have to be variables. And here there is no variable. This is a constant. So there is no free variable. So the set of free variables is empty. Now, what happens if I have the second case? So now it's not a constant, but a variable. So some variable x. For x is a variable. Well, okay, there's just one variable in this term, namely x, and it is free. I mean, there is no lambda anywhere, so it's not bound. So the only free variable here is x. Now, what happens if I have an application? So I want to know the free variables in a lambda term of this form, where t1 is applied to t2. Well, here I just take the free variables from t1 and the free variables from t2. So this is defined as the free variables of t1 united with the free variables of t2. And the only slightly interesting case is this one. If I have the free variables of such a lambda abstraction, lambda x dot t, which variables here are free? Well, I take all the free variables from t, but not x, because x is bound here. So all the free variables from t without x. So for example, if I want to know what are the free variables in the following lambda term, lambda y dot yx. So what does this mean? Well, intuitively, this means this takes a function y and applies it to the argument x. This is the higher order function which takes a function and wants to find out what is the result of this function at the position x. So what are the free variables here? Well, all the free variables from yx, but not the one that is bound by the y. So the only free variable here is x. And if a lambda term has no free variable, we say that it is a closed lambda term. So a lambda term without free variables is called closed. Without free variables is called closed. So this one is not closed because this variable x is not bound. Okay, and now since we know this concept of free variables, we can also define the concept of substitution. And a substitution means I take a lambda term and I can instantiate its variables, but only its free variables, not its bound variables. And I will define this in a minute, but before I have to wipe the board. And since I will wipe out the definition of lambda terms, I will put it here on the slide. So this was the definition of lambda terms. For a full programming language, this is pretty short. It easily fits on half a slide. Okay, so now the next step to explain what lambda terms mean and how to operate with lambda terms is to define substitutions. And when we do this, so the goal is to define substitutions operating on lambda terms. And before we do this, we should think about, again, what intuitively such a lambda term means. And if we have such a lambda abstraction, this stands for a function. I mean, this lambda x dot t means it's the function that takes x and maps it to the result t. And now, for example, if what these substitutions should do is they should replace or instantiate every free occurrence of a variable of variables by other terms. So, for example, we write if r is a lambda term and x is a variable and t is also a lambda term, then we write this for the result of applying this substitution to this term. For the result of applying the substitution which replaces x by t, so this substitution which replaces x by t to the lambda term r. So for example, let's consider an example. Let's say r is the following lambda term. It is lambda y dot yx, for example. And let's say t is the term lambda u dot uv, and x, y, u, and v are variables. Then what is r if I replace x by t? Well, it's this term r, but I replace all free occurrences of x by t. So this x here must be replaced by t. So then it is lambda y dot y, and now lambda u dot uv. Okay, this is of course not surprising. But if we now think about what these terms mean, this is the function, the higher order function, which takes the function y and gives me back the result of y at the position x. Now, it doesn't really matter whether I call this argument y or whether I call it differently. So r should be equivalent to the following term r prime. And r prime is almost the same as r, but I just rename this bound variable. So whether I call this y, or whether I call this z, or whether I call this y prime, that shouldn't really matter. So both r and r prime represent the higher order function that takes an argument, a function, and gives me back the result of this function at position x. So both r and r prime take a function. One time is it called y, and one time it is called y prime. Take a function and return the function's result at position x. The function's result at position x. So in other words, the names of bound variables don't matter. It doesn't matter whether I call this y or whether I call this y prime. So the names of bound variables don't matter. They do not matter. And since r and r prime are essentially the same, if we apply substitutions to them, it should also be the same. So it shouldn't matter whether I take r and use the substitution, or whether I take r prime and use the substitution. So r with x replaced by t should also be equivalent to r prime with x replaced by t. And this should work, of course, for any variable x and for any term t. But what happens if I don't take this term t, but I take a different term? So let's take not the term t, but let's take a term t prime. And t prime is the following term. So t prime should be the term lambda u dot u, and now not v, but y. So now by accident, this variable y, which was the bound variable in R, occurs in this term t prime. That's pure chance. That's pure coincidence. It doesn't really matter whether I call this y or whether I call this y prime, but now it seems to matter because this variable y occurs in t prime. So if we apply substitutions as before, then there is a problem, because then if I take r and replace x by t prime, then I get, well, lambda y dot y, lambda y dot y, and now I have this term here, lambda u dot uy. And if I do the same thing with r prime, then I have y prime here, and here I have lambda u dot uy. And now these two lambda terms are not equivalent, because this lambda term is closed. It has no free variable. This y here is bound by this lambda, whereas this term here is not closed. This y here is not bound by anything, because here only y prime is bound by the lambda. So this is a closed lambda term. So this lambda y also binds the free variable y of t prime, and this is not closed. And that's not good, because how I call closed variables, that shouldn't really matter. It shouldn't matter whether I take r or r prime. The result of applying a substitution should also be equivalent. So this is bad. This is bad since the names of bound variables shouldn't matter. they should not matter. And so the solution is we will define substitutions in such a way that they really do not matter. So whenever we apply a substitution and we replace some variable x by some term t, and t has a free variable, then this variable should not be bound by some lambda that occurs in R. And if this would happen, then we first rename the bound variables in R. So to solve this problem, we proceed as follows. If there is some variable in the free variables of t which gets bound by some lambda y in R, then first rename the bound variable in R. So this means if we take the terms that we had before and we want to replace x by t prime, then we see that y is a free variable of t prime. And this y would get bound by the lambda y in R. So by this lambda y here. So what we do then is we first rename this y here to something fresh. For example, to y prime. So rename lambda y to lambda y prime. So we first rename this y here to y prime. So then it looks like this. And then afterwards, we apply the substitution. And so the result here will also be lambda y prime, and now lambda u, uy. So this is the important part of these substitutions. Apart from this, substitutions on lambda terms work as expected. So let's define this formally now. So this is definition 313 for substitutions on lambda terms. So we have two terms r and t. These are lambda terms. And we have a variable x. And now we define what happens if we replace the variable x by t in the term r. And again, we do this for all possible cases. So here on the slide, you can see how lambda terms could look like. So the first case is the lambda term is a constant. So if I have a constant and I want to replace all free occurrences of x by t, then nothing happens because this constant contains no free variables. So it just remains unchanged. So nothing happens here. Now the next case is that we have a variable. And now, of course, there are two possibilities. Either the variable is x or the variable is different from x. So if I have the variable x and I want to replace x by t, then obviously the result is t. And if I have a variable y, which is not x, and I want to replace all occurrences of x by t, then nothing changes, and I just keep my y for all variables y which are different from x. Now the next case are applications. So suppose my term looks like this. R1 is applied to R2, and I want to replace all free occurrences of x by t. Well, then I do this in R1 and I do this in R2. So this is replace all free occurrences of x by t in R1 and apply the result to the same thing with R2. And here R1 and R2 are lambda terms. Okay, and the last case is a lambda abstraction. Now, of course, here we just want to replace free occurrences of x. So let's first regard the case where x is bound in the lambda abstraction. So if I have a term like this, lambda x dot r, and I want to replace all free occurrences of x by t, then I can clearly see that there is no free occurrence of x because, well, x is bound here by the lambda. So nothing changes. We just keep the term lambda x dot r. Now what happens if the variable that is bound by the lambda is not x, but some other variable y? And I want to replace x, all free occurrences of x by t. Well, essentially, I apply this substitution just to the body of this lambda abstraction, to R. So this lambda y remains there. And here, I apply the substitution just to R. And this works if y is different from x. And, well, we have to make sure that this conflict with the names does not appear. So in this example up here, we had the problem that there was a variable which occurs free in t, so in the term that we introduced by the substitution. And this y should not get bound by the lambda. So in other words, we have to make sure that the y, which is bound by the lambda, does not occur free in t. So we can do this as long as y does not occur in the free variables of t. And now the remaining case is what happens if y does occur free in t. So what happens if I want to apply the substitution, but this time, so again, y is different from x, but this time y does occur free in t. So what do I do now? Well, I make sure that this y which occurs in t should not get into the scope of the lambda. So what I can do is I can rename this bound variable. Instead of calling this y, I can call it y prime. So instead of calling it y, I will now call it y prime. And then, of course, I also have to replace all y's in here by y prime. So I take r, but I replace all the y's by y prime. And now I have a copy of this original term, but all bound variables y are now called y prime. So now there's no conflict anymore. And so now I can apply this substitution x instantiated by t to this term. And of course, this y prime has to be fresh. So this y prime should be a fresh variable. So it should not occur in the free variables of r, and it should also not occur in the free variables of t. So this just means take a fresh variable, which has no conflict with the previous free variables that we had. So if we have this, then indeed, if in our example we take r, what was r? It was lambda y dot yx, and we want to replace the x by lambda u dot uy, then we first have to rename this bound variable. So we rename this bound variable to y prime. And we have to do this renaming also in the body of the lambda abstraction. And now we apply the substitution to this here, and now everything works smoothly, and we get lambda y prime dot y prime applied to lambda u dot uy. So this definition of substitution makes sure that there are never any name conflicts. And if there were name conflicts, then I rename bound variables. And this concludes the part on the syntax of the lambda calculus. Now we know how this programming language looks like. We know how to manipulate terms by substitutions. And this will be enough to define the semantics of the lambda calculus. And that comes after I wipe the board. So you can see that this works much faster than with Haskell. I mean, to introduce the syntax of Haskell, it took us the whole chapter 1, so like a month or 1.5 months. Here it takes us, well, half a lecture. And also the semantics we can do in the other half of the lecture. So instead of devoting 2 months to it, like with Haskell, it's sufficient to devote 1 lecture to it. On the other hand, if you write actual programs in the lambda calculus, they look not as readable as in Haskell, of course. Okay, so let's move on to the semantics of the lambda calculus. And the semantics will be defined by so-called reduction rules. So these reduction rules, they tell us how to evaluate a lambda term. And this, we say that one lambda term is evaluated 1 step to the next lambda term. This step we call reduction. So we now introduce the reduction rules of the lambda calculus. And well, these reduction rules, they describe the operational semantics. So they describe a kind of interpreter which evaluates lambda terms. And we say, well, this interpreter does the right thing, so this defines what the semantics of a lambda term is. So they are used to define the operational semantics of the lambda calculus. And we will use 3 reduction rules, 3 kinds of reduction rules, and traditionally they are named by Greek letters. So I mean, lambda calculus has already this lambda in there, so it's natural to give also Greek letter names to these reduction rules. And the first reduction rule is called alpha reduction. So this is the first reduction rule. It's called the alpha reduction. And what does alpha reduction do? Alpha reduction is used to rename bound variables. So it's something like what we did up there when we discussed substitutions. You can, for example, rename a bound variable y to another bound variable y prime. This step is called alpha reduction. So let's define it formally. So the alpha reduction relation, we denote this by an arrow with an index alpha. This is a relation between 2 lambda terms. So you can transform 1 lambda term to another lambda term by this relation. So it's a relation between 2 lambda terms. And how is it defined? It is defined as the smallest relation such that. So what can you do? You can rename bound variables. So if I have a lambda term like this, lambda x dot t, I can rename this x to something else. So I can, by alpha reduction, I can rename it to some other variable, for example, to y. But if I rename this x to y here, then I also have to do this in the body of the lambda terms. So I have to replace all free occurrences of x by y. In other words, I have to take t, but I replace all x's by y. And this is only allowed if this variable here is fresh. So this variable should not occur free in this term t. If y is not free in t. And all of these reduction rules you can not only apply on the top level of the term, but you can also apply it to subterms. So if you already know that t1 can be reduced to t2 by alpha reduction, then you can also do this if t1 and t2 occur deep inside your term, so if they are really subterms of your whole term. So for example, it could happen that t1 occurs on the left-hand side of an application, and if t1 could be reduced to t2, then this also works if t1 is just on the left-hand side of an application. So you can also reduce this complex term to this complex term. And you can do this not only if t1 and t2 are on the left-hand side of an application, but it also works if they are on the right-hand side of an application. And it also works if they are in the body of a lambda abstraction. So if you have some lambda abstraction, lambda z t1, then I can reduce this to lambda z t2 for all terms r and all terms and all variables z. So this means the reduction rules can also be applied on subterms. Can also be applied on subterms. So what does alpha reduction do? It just renames bound variables. Alpha reduction just renames bound variables. That's the idea of alpha reduction. So if we want to see an example, well, let's take lambda xy dot xy. So this stands for the function that takes a function x and an argument y and gives you back what happens if I apply x to y. So what can I do with alpha reduction? Well, I can rename bound variables. Now both variables here are bound. X is bound, y is bound, so I can rename any of them. So for example, I could, by alpha reduction, reduce this to lambda x prime y, x prime y. And if I want, I continue further, and maybe I also get lambda x prime y prime, x prime y prime. And of course, I can also undo these renamings. So if I want, I can also go back and rename this x prime back to x if I want. And of course, I can also go back and rename y prime back to y, and so on. So many possibilities here. So what you can see is that this relation is symmetric. So if I can go from t1 by alpha reduction to t2, then I can also go back from t2 to t1 because they only differ by renaming the bound variables. So this is obviously a symmetric relation. So this relation is symmetric, and therefore one sometimes also calls this not alpha reduction but alpha conversion. Therefore this is also called alpha conversion. And the idea is that terms that are the same up to alpha conversion, they are considered to be equivalent. They stand for the same function. So terms that are identical up to alpha conversion are considered to be equivalent. Up to alpha conversion are considered to be equivalent. So with alpha reduction or alpha conversion alone, well, you can just rename bound variables, but that's it. So really evaluating things doesn't really work yet. So we need more reductions. And well, the Greek alphabet is not finished yet. And what's the next letter in the Greek alphabet? It's beta. And so the next reduction rule is called beta reduction. And that's the most interesting one. So the next reduction rule is beta reduction. And beta reduction, that's the one that allows you to apply a lambda abstraction to some argument. So the idea is, let's apply a lambda abstraction to an argument. So that's the most interesting thing. And how does that work? Okay, we come to beta reduction. So this is definition 3.2.2. Beta reduction. And again, this is a relation on lambda terms, so you can transform one lambda term to another one by beta reduction. So as before, the relation arrow beta is again a relation between two lambda terms, and it is the smallest relation with the following property. Okay, so how does that work? So as I said, the idea is we want to apply lambda abstractions to terms. So we have some lambda abstraction, something like this, lambda x dot t, and we want to apply it to a term r. So how does that work? What should the result of this be? Well, I mean, this should be familiar to you because the lambda calculus is really a subset of Haskell. So if you think of backslash here and of arrow here, then this is a Haskell expression. And you know what happens in Haskell if you write this. This is considered to be a function which maps x to t. And now as the argument x, we take this r. So the result will be t, but all the occurrences of x here will be replaced by r. So the result of this is t, but all three occurrences of x are replaced by r. That's it. So this is the essential heart of the lambda calculus. If you understood this, you understood the essence of it. And that's enough for a whole programming language, surprisingly. So, and you can apply this not only on top level, but you can apply it anywhere. So if this term occurs somewhere deep inside your term, you can still do this reduction. So if you know that T1 reduces by beta reduction to T2, then this also works if T1 is on the left-hand side of an application, and it also works if T1 is on the right-hand side of an application. And it also works if, how did I write it? It also works if T1 and T2 are in the body of a lambda term. So let's make some examples. So let's apply this lambda term to this lambda term. So 0 is a constant. That's fine. Constants are also lambda terms. And this is also a lambda term. And so according to this definition, what will be the result of this? So I can do beta reduction. The result will be the body of the lambda term. So it will be x. But I have to replace all occurrences of x by 0. So in other words, it will be 0. And this is what you would expect, because this is the identity function. It's the function that takes an argument x and gives you back x. So it maps x to x. That's the identity function. So if I apply the identity function to 0, I get 0. OK, another example. Now let's make it a bit more complicated. So let's take something which is not so readable, lambda xy dot xy, and we apply this to y. Now this is nasty because by coincidence, this y that we want to apply it to already occurs here as a bound variable. That should not happen. And if it does happen, then we rename this y here. So we first do a kind of alpha conversion step and replace this y here and here by y prime. So this and this will become y prime. And then we can apply the beta reduction as before. So we take, the result will be x, y prime. So the result will be, OK. So in other words, this is considered to look like this. It's lambda x dot lambda y prime dot x y prime. And now what will be the result? The result will be this thing. So it will be lambda y prime dot x y prime. But all occurrences of x will be replaced by y. So in other words, it will be the term lambda y prime dot y y prime. So beta reduction makes sure that there are no conflicts here, and if there were conflicts, things are renamed. This is just because of the definition of substitutions. Let's make one more example. So maybe a larger term. So lambda x dot plus x1. So if you want, this stands for the function that increases its argument by 1, the successor function. And I want to apply this to the following term, lambda y times yy, and this is applied to 3. And now you can see there are two possibilities. If I want to do beta reduction, I could apply beta reduction on this subterm here. So let's look at all possibilities. So what should I do? Should I apply beta reduction at the outside or at the inside? Well, both is possible. If I apply beta reduction at the inside, then I would apply this lambda term to this thing over there. So this lambda x plus 1 would remain unchanged, plus x1. But here I would get the application of this term to this term, so this would be times 3. So this would be a beta reduction step. And now this can be evaluated further. And what do I get? I get plus applied to times 3 and 1. So I get plus applied to times 3 and 1. So this would be an innermost evaluation. Now Haskell would rather do outermost evaluation, so I would apply this outermost lambda abstraction to this term over here, and then I get plus, and here I have lambda y dot times yy 3, and this thing is applied to 1. And if I do one more beta step, then I evaluate this inner application, and then I get plus times 3, and then 1. And then I was lucky because it didn't matter whether I go this way or this way, I arrived at the same result. So that was nice. So we can see that there can be several ways to evaluate a lambda term. a lambda term, as we can see here. And in this example, it didn't matter which way we go, we arrived at the same result. And of course, the question is this always the case? Does every evaluation always yield the same result? Always yield the same result? Well, that's a question that Church asked himself as well when he invented the lambda calculus in the 1930s. And he solved the question, and I will tell you the solution also after I wipe the board. Okay, so to formalize this question more precisely, let me introduce some easy notions, namely the notions of transitive reflexive closure, the notion of normal form, and the notion of confluence. And with these notions, we can ask this question more precisely. So these notions, they are not specific to the lambda calculus. So these notions make sense for any relation, and therefore let's define them in a general way for any possible relation. So let's suppose we have some relation arrow on some set n. Of course, here we are mainly interested in something like beta reduction on lambda terms, but these notions can be defined for any relation. So let this be a relation on some arbitrary set n, be an arbitrary relation. And then we can define the transitive reflexive closure of this relation. And we denote this by writing a star above this relation. So this is the transitive reflexive closure of this arrow relation. The transitive reflexive closure of this arrow relation. And what is this? It is the smallest relation with the following properties. So 3 properties. The first property is this relation contains the original relation. So if T1 stands in relation with T2 in the original relation, then it also does that in the transitive reflexive closure. Then also T1 stands in relation with T2. So in other words, it means that this relation is a subrelation of the new one. And the next property is, it says that the star relation is transitive. So if I can go in one step from T1 to T2, and in many steps from T2 to T3, then I can also go in many steps from T1 to T3 directly. So this states transitivity. And the last point is reflexivity. So every element stands in relation with itself. So this is reflexivity. So in other words, what the star relation means is the following. So in other words, T0 stands in relation, in the star relation with Tn, if there are objects such that T1 stands in relation with T0 stands in relation with T1, T1 stands in relation with T2, and so on, and we go n steps, where n is greater or equal to 0. So this is just the meaning of the star relation. So if you think of this as evaluation, then this means T0 can be evaluated to Tn in arbitrary many steps. 0 steps, or 1 step, or 2 steps, or 3 steps, as many as you want. So that's the meaning of this transitive reflexive closure. Now what's the meaning of normal form? So this was the transitive reflexive closure. Now let's define what a normal form is. A normal form is an object that you cannot evaluate further. So it's an object that has no successor in this relation. So an object Q is a normal form if there is no other object Q prime such that Q stands in relation with Q prime. So if you think of this arrow as evaluation, then these are the objects that you cannot evaluate further. This is where evaluation stops. And also makes sense to say that some object is the normal form of another object. So we say that Q is a normal form of another object T, of some object T, if the following holds. I can evaluate T to Q in arbitrary many steps, and Q is a normal form. So in other words, if you think of the arrow as evaluation, then this means this is the result of the evaluation. If I take some complicated expression and I start evaluating it, then this is the result of the evaluation. And here, evaluation cannot continue any further. This is a normal form. And now the question is, can it happen that some term has more than one normal form? Because this is what happened up here. We had this complicated plus and times term, and we evaluated it to normal forms. So here evaluation stops, and here evaluation stops as well. So these are normal forms of my original term. And in this example, this term has only one normal form. And the question is this always the case, or could it happen that a term has two normal forms, or even more? And this is the question, essentially the question of confluence. So a relation is called confluent if the following holds for all objects T, Q1 and Q2. So suppose I can evaluate T to two different objects. I can evaluate T to Q1, and I can evaluate T also to Q2. So if T can be evaluated in several steps to Q1, but T could also be evaluated in several steps to Q2, then confluence says that this is harmless. I mean, this can happen, but this indeterminism I can resolve because there's another object, Q, such that Q1 can be evaluated further to Q, and Q2 can also be evaluated further to Q. So they have a common successor. So if this holds, then there exists another object Q such that Q1 can be evaluated further to Q, and also Q2 can be evaluated further to Q. Now this can be depicted graphically. So this is the object that I start with. And if this object starts an indeterminism, so I can evaluate this in several steps to Q1, but I could also evaluate this in several steps to Q2. And then confluence means that whenever I have such a indeterministic situation, then I can bring this to a common successor again. So both Q1 and Q2, they can be joined again. So there exists some common successor Q, so that I can go from Q1 to Q, but I can also go from Q2 to Q. And confluence means if the solid arrows exist, then the dotted arrows exist as well. So this means if the solid arrows exist, then the dotted arrows exist as well in this graphics. So this is confluence. And now you might ask, why am I interested in confluence? I mean, the real question is, does the evaluation always result in a unique result? Or can it happen that some term has two different results when I evaluate the term? So the question is, how many normal forms can a term have? And if I have confluence, then I can be sure that every term has at most one normal form. And that's the statement of the following easy lemma. So confluence is what I really want, because confluence implies unique normal forms. So what this means is that if I have a relation that is confluent, let this be a confluent relation, then every object has at most one normal form. And well, this is a very easy proof of two lines. And to give you something to think about it, I will not present it now, but you can think about it over the weekend, and I will show it to you on Monday. But really, this is a two-line proof, so this is very simple. OK, so we meet again on Monday.